last time, we derived the Hamiltonian for electron-phonon coupling. And today we will continue calculating the corrections to the total energy and also to electron and phonon energies that contributed from electron-phonon coupling. And first, let's just calculate the correction to the energy, the excitation energy that is contributed from the electron-phonon coupling. And assuming that electron-phonon coupling is a weak perturbation, and so we could treat this HEP, electron-phonon Hamiltonian, as a small perturbation. And we do perturbation theory in this HEP, and we could expand this based on the non-perturbed eigenstate, where non-perturbed eigenstate contains, n electrons carrying momentum k, and also nq longitudinal phonon. And that is this phi here, which is the unperturbed ground state. And this HEP acts as the perturbation. And we can perturb this up to first order, which is the linear in HEP. And also we could continue expanding this up to second order in HEP. So let's just calculate this first order corrections to the energy, which is this expression value of HEP sandwiched by this unperturbed ground state phi. And as we already mentioned many times, that this HEP has the form of this electron-phonon coupling, which is proportional to this C dagger C density operator coupled to this creation or destruction of a single phonon, B plus B dagger. So once we insert this HEP to the linear term, then this destruction and creation of a single phonon will actually change the number of phonons of the unperturbed ground state by 1. Okay? And therefore, this part of the state contains this phonon minus 1. Okay? But the left side of this unperturbed ground state contains still NQ longitudinal phonon, and therefore, by orthogonal normalization condition of the ground state, this matrix element vanishes because, you have different particle number on the left compared to the right, and therefore their inner product should vanish. So the leading term that gives us a non-trivial result comes from the second order perturbation, epsilon 2, where I simply just expand all this electron-phonon Hamiltonian and this energy denominator, and we get this messy expression here. And the job we need to do is to evaluate this excitation value. So we have, say, 3 operators on left, another 3 on the right, and there's the energy denominator from the second order perturbation. And we sum over all this, momentum k and k prime, and k double prime, k triple prime. So as we mentioned many times in the past, that to deal with such expression value, we need to make this operator the number operator. Okay, so we should pair all these operators in such a way that they become this number operator, occupation number operator. Then we can sandwich this occupation number operator by this Dirac-Broglie state on the left and Dirac-Katz state on the right of this unperturbed ground state. And then we get a bunch of Fermi-Dirac or Bose-Einstein distribution function. Okay, so that's the trick. And so we know that the non-zero contributions occurred only if we have such a symmetry. Whereas k triple prime is the same as k, and k double prime is the same as k prime, so that this matrix element m k double prime k triple prime is the same as m k prime k, okay, and also which is the m dagger k k prime, and therefore this matrix element on the right and the left could be combined together and to form m square. Okay, the magnitude square of m kk prime. And then we could separate this non-zero contributions into two parts. Okay, so this is the first term, and this is the second term. So as we have done already in the past chapters, that we should form this occupation number for boson operators, also for fermion operators. And this is the cartoon diagram to illustrate how these operators could be formed paired. Okay? For example, this initial state contains electron with momentum k, and then we have another phonon carrying momentum minus q, and these two operators get scattered, and then in the intermediate state you get one electron carrying momentum k prime, and then this electron is destroyed later, and then two particles coming out. One is electron carrying momentum k. It's created. Another is phonon carrying momentum, say, minus q is created. Okay? So the only thing that we need to worry about is the energy denominator. This is the operator 1 over this initial state energy, epsilon 0, and subtracted by this H0 operator, which is the unperturbed Hamiltonian. And you can very easily see that for the first diagram, the energy denominator is actually total energy of the initial state, which is the sum over these two energies, electron and phonon. And this H0 operator is going to act onto the intermediate state, which is the energy of this single electron with momentum k prime. Okay? And for the second process, you could actually do the same thing. What is the energy of the initial state, epsilon 0? Well, there's just one electron as an incoming particle. So epsilon 0 is actually epsilon k. And what is the intermediate state energies, which is the sum over these two particle energies, which is h bar omega q for the phonon, and also epsilon k prime for electrons. So you simply just plug in this energy denominators back to this matrix element, and remember you should form pairs between, say, boson creation and destruction operator, and also fermion destruction and creation operators. Of course, you need to take care of the commutation, the ordering of these operators, satisfying both the commutation rules for boson operators and also anti-commutation rules for fermion operators. And same for term 2. So we could just combine these two terms. We could just form pairs of the boson operators, also fermion operators. And when we combine these two contributions, we get this expression here. There are two contributions. This is the first term, and this is the second term. And there's a common factors, which is, this expression value of a Fermi-Dirac distribution, and k times 1 minus nk prime, which comes from the pairing of this, C diagram C with the proper ordering, and this anti-commutation rule is also taken care of. And this factor, this Fermi function, multiplied by the this complicated energy denominators and this numerator containing this boson occupation number n minus q, and also nq plus 1. Okay, so the origin of this n minus q comes from the pairing between b dagger minus q and b minus q. So you should actually, form pairs, and by jumping this b minus q, all the way to the right side of the b dagger minus q. And same for this, the second term, there's an additional constant 1 added to this m of q. This 1 comes from the commutation relations for of bosons, because you need to actually go all the way to move this bq all the way to the right part of the B dagger Q. When you do so, there's an extra constant 1 picking up by this commutation rules for boson operators. So I suppose that you should be able to derive such expression here. Okay? And we could actually manipulate this complicated terms like this by adding and subtracting the term which we call delta, which is given by this complicated function containing this matrix element square and energy difference between two electrons, epsilon k and epsilon k prime, and also this Fermi or Bose factors. Okay? And this delta, when you sum over k and k prime, you can show that this vanishes. It doesn't change anything because this delta is actually odd function in k. When you interchange k and k prime, where both k and k prime are momentum indices to be sum over, when you switch the order between k and k prime, you can show that delta goes to minus delta, and therefore, when you sum over both k and k prime, this delta vanishes. Okay, so you add a delta which is 0 and subtract by the same amount, and you can get this final expression here. Okay, so we will comment on these two terms in just a moment. Okay, so in summary, this total excitation energy containing electron-phonon effect has this second-order contributions, which is the product of this Fermi-Dirac distribution function and this phonon occupation, which is the Bose factor. And also there's non-trivial energy denominator, which is the square of the epsilon k minus epsilon k prime, subtracted by this phonon energy square. And similarly for the second term. Okay, so this looks horrible, but fortunately we could simplify this calculation after the break, and we could make some remarks and comments on this revisions or corrections to the photon frequency and also electron excitation energy from this general expression here. So let's take a short break. Okay, so let's continue analyzing this modified energies, total energies in this electron-phonon system. Okay, so we have derived this total energy up to second order in perturbation, and now we could use that energy to calculate this phonon frequency change or phonon energy change. So this h bar omega p phonon carrying momentum q is defined as the derivative of this total energy, including electron-phonon contributions, with respect to this phonon occupation number, okay, which is the energy of a single phonon, because this is just total energy and divided by the number of phonons, roughly speaking. Okay, so this corresponds to the single phonon energy or single phonon frequency omega pq, and this is given by this unperturbed the phonon energy h bar omega 0q, and then there's a correction -2 times this complicated function which comes from the electron-phonon coupling term. Okay, so let's just take a look at the slope of the derivative of this h bar omega p in momentum space. Okay, so we could take the derivative of this frequency of a single phonon omega pq with respect to this q at a particular value of a q, which we call q star. And remember, this q is given by k minus k prime, which is the momentum transfer between these two electrons at different momentum. Okay, so in deriving this approximated form of this single phonon energy, we use the assumption that the electron energy is much larger than the phonon energy, and as a result, in the energy denominator, we sort of use that approximation, which means that h bar omega q is much smaller than this energy difference between two electrons at k and k prime. So we could therefore, simplify this single phonon energy, this way. So let's just take the derivative frequency of the single phonon with respect to this momentum q at a particular value q star, and you could simply just take this derivative, and you find that this is given by this matrix element square times nk, and the square of the energy difference in the denominator, and multiplied by derivative single electron momentum k minus q, respect to q star. Okay, so let's just finish this calculation. So what is this epsilon k minus q? Well, this is nothing but the single electron excitation energy, right? And you take the derivatives single electron excitation energy with respect to q at particular value of q star, and this is what you get. Okay, so let me just rewrite this derivative of the single phonon frequency in this form, which will become more clear in just a minute. Okay, so you could simply just simplify this energy denominator, which is q stars square times 2k minus q n square, because this cancels with this k, and this 2k's are add up, right? Okay, so then you could study this derivative, which is the slope of this single phonon frequency at particular value of q star. Okay, in particular, you can see very clearly that there is a possibility that this derivative diverges, which means that when q star is very close to this 2kf, okay, because most the active electrons are close to the Fermi surface. So when you sum over k here, so the most contributions at low temperatures will be the electrons very close to kf, and therefore this denominator 2k minus q star, when q star is approaching 2kf, and this energy denominator vanishes, right? So when k approaches kf, which is the case for low temperature metals, and when q star is close to 2k and k close to kf, which means that when q star is close to 2kf, you can very clearly see that the energy denominator vanishes. And it vanishes as a speed of 1 over k minus kf squared. So it's very, very pronounced divergence, okay? Very serious divergence when k is close to kf. All right? Good. So, and that's the phenomena which we call this Coulomb anomaly. We'll see just a moment in the diagram. We can compare the dispersion of electron state and also dispersion of the phonon, and how this happens. Okay, so let's just look at this cartoon pictures of the electron Fermi surface and also the phonon dispersion relations versus q, the momentum transfer. So this delta k close to 2kf scattering that we just mentioned is a very efficient scattering of electrons by exchanging the energy of momentum with phonon. Okay, so this Coulomb anomaly could be understood in terms of the electron scattering across the Fermi edge. Okay, so suppose one electron carry momentum kf, and another electron carry momentum minus kf. So these two electrons on two edges of this Fermi surface are interacting with each other by exchanging the phonon. So the momentum change of these two electrons across the Fermi edge is precisely 2kf. And that momentum change is precisely this limit when q star, which is the energy difference between two electron states, k minus k prime, which is 2kf. So these two electrons exchange their momentum, and the momentum transfer between these two electrons is precisely 2kf, and this 2kf is precisely the phonon momentum. Okay, so if you look at this phonon dispersion on the right, you'll see that this phonon looks like just a quadratic band versus momentum q. But when q approaches 2kF, there's a sharp, singularities, right at this 2kF scattering. Okay, so this singularities of the phonon band or phonon dispersion is called Coulomb anomaly, and this Coulomb anomaly has been observed in many materials, which shows phonon mode. And the reason of this Coulomb anomaly is what I just mentioned, that it is due to the softening of lattice. Lattice vibration at low energies is getting enhanced because their electrons near the two edges of the Fermi surface come into play. Okay, so electrons and phonons exchange momentum of 2kF, and this 2kF scattering causes this singularities of the slope of the phonon frequency right at 2kF. Okay, so this is the first consequence, non-trivial consequence of the electron-phonon effect on the phonon dispersion. So the phonon dispersion gets modified because of this 2kF scattering with electrons. So you can see that because of electron-phonon coupling, the phonon dispersion get modified. And that's the first non-trivial effect of the electron-phonon coupling. So let's take a short break. When we come back, we will study the other side of the correction, which is the correction to electronic excitation energy. So let's just do the following calculations. And we have already calculated the phonon dispersion and phonon frequency due to electron-phonon contribution. Now let's just do the other estimation, namely the electron-phonon coupling that leads to the change of the electron mass and also electron dispersion. So, and we call this Polarons, which is addressed electrons by this electron-phonon coupling cloud. But let's just do it at 0 temperature. When temperature is 0, this phonon occupation is frozen because this is a Bose factor. And so the total energy up to second order in perturbation is given by epsilon 0, which is the pure electron kinetic energy, and plus this electron-phonon contributions at 0 temperature, and therefore there is no NQ here. Okay, NQ term is gone at 0 temperature. So let's just evaluate this single electron excitation energy by taking the derivative of the total energy with respect to this electron occupation number, following the same way that we calculate this, single phonon dispersion. And you get this free electron kinetic energy, epsilon k, plus some additional term that comes from the electron-phonon interaction. Okay, there are two contributions. Okay, you could very easily verify that this is the case. So let's just combine everything. So you could very easily see that single electron excitation energy is given by this non-interacting part plus the electron-phonon contributions. So there are two terms that contribute to these corrections. The first term is independent of Fermi function, which is simply just 1 over the energy difference between electron and momentum k and k prime, and also minus h bar omega q. And this term always exists. So this exists even for insulator. And we call this Polaron contributions. And the second term depends on this Fermi function, which exists only in metals, because we carry this Fermi function. Okay, so what is the Polaron? Well, as you can see from this cartoon picture, that the electron move around this lattice, but the lattice can vibrate, right? And the phonon of the lattice vibration coupled to the electron. So you can consider that the electron is dragged by this phonon cloud in the neighborhood. So if you look at this any electrons in solids, the electrons will couple to the nearby ions because the ions vibrate, and the vibration of ions are nothing but phonons. And so phonon and electron couple together, and in real space you'll see that electrons actually are not fully independent anymore because electrons are dragged by this ion clouds, and in particular the ions carry positive charge. An electron carry negative charge. So there is the polarization fields, electric field in that cloud. And so we call this, the whole thing, Polaron, which by definition is a charged particle combined with the nearby polarization fields. Okay? So the charged particle is the electron itself and also some positive charge ion clouds. And the polarization fields is nothing but the electric field induced by this electron-ion coupling in the neighborhood of electrons. So electrons get heavier because electron cannot move independently because the electron-phonon coupling. And you can see this very clearly by looking at the dispersion of a single electron excitation. And from this, the first term of the correction here, you can very easily see that this electron actually coupled to phonons because the energy denominator shows both electron and phonon energy. And we call this dressed up electrons. Okay, electrons are wearing clothing, okay, because of this coupling to the ion vibrations. So let us look at this consequence of this polarons or dressed electrons by looking at this modification of the Fermi surface of the electron dispersion. And electron dispersion is given by the non-interacting part plus the electron-phonon contribution, which I call this, this messy formula inside the yellow box, f of epsilon k function. And you could, evaluate the slope of the electron dispersion, which is the velocity of electrons. So the velocity of electrons is given by the gradient of this electron dispersion, and it consists of two terms. One is the free electron part, which we know very well, and the second term is a new contribution from electron-phonon coupling. And if you evaluate this, the derivative of this complicated f function, you will see that this contributions estimated close to the Fermi surface, and this contributions is, say, minus 2h bar times the average frequency of phonons, which we call this omega bar, and times the density of states of electron at the Fermi surface, and the average matrix element and bar square times the derivative of this integral with respect to the epsilon k. Okay, this integral is given by this by change of variables, the eta, where eta is defined as the energy difference between epsilon k prime and epsilon k. And you could change variables to eta, degrees of freedom, and we'll see just a moment that this integral could be evaluated pretty straightforwardly, and then you take the derivative of this integral. Okay, so let's take a short break. When we come back, we will finish up this Fermi velocity modifications due to the electron-phonon coupling. So let's take a short break. Okay, so let's finish this electron effective mass calculation. So as I mentioned, because of electron-phonon coupling, the velocity of electron also get changed. And there's additional contributions from electron-phonon coupling, which is given by the second term here, where we have integral over eta, and eta is defined as epsilon k prime minus epsilon k. And after this integral over the eta, we need to take the derivative of this integral with respect to the epsilon k. And with the help of this new change of variables, these Fermi functions n of epsilon k prime could be rewritten in terms of the Fermi function of eta plus epsilon k. And so the Fermi function is a step function, a zero temperature which the this value of Fermi function is 1 below the Fermi surface and 0 above the Fermi surface. And the condition that Fermi function drops from 1 to 0 is when this condition is satisfied. This eta plus epsilon k is given by epsilon f. And so if you take the derivative of this Fermi function, it is known that you have this minus Dirac delta function right at the Fermi energy, right? And we take advantage of such a nice property of the Fermi function, and we can get this evaluation down, and we plug in this properties of this Dirac this delta function when we take the derivative of this Fermi function with respect to epsilon k, and evaluate this integral combined with the Dirac delta function, you'll get this result. Okay, so the modified Fermi velocity VEK is given by the unperturbed free electron velocity times 1 plus this correction due to electron-phonon coupling, and this correction as this numerator and denominator, and the numerator is this 2h bar omega bar times density states of electrons and matrix element square, divided by this denominator, which is the energy difference square, epsilon k minus epsilon f, and minus this phonon energy square. And you could very clearly see that this electron dispersions got modified because of this additional term. And in particular, this modification is very severe when the denominator vanishes, which means that you get some singularities when this happens, which means that epsilon k minus epsilon f is actually plus or minus h bar omega bar. Okay, so this is precisely what I mentioned just here, that the energy denominator vanishes, which leads to the divergence, when this eta is actually plus minus h bar omega bar, which means that when this electron energy epsilon k relative to the Fermi energy is actually plus or minus h bar omega bar, which is the phonon energy, and this energy denominator vanishes, and therefore you get some enhancement of this correction due to electron-phonon coupling, and this enhancement factor is called alpha. So if I simply just plug in this condition and simplify this expression, I get this. The new velocity of electron is given by the unperturbed one times 1 minus alpha, and this alpha is defined here. All right, so there's an important minus sign here, and this alpha is actually positive value. So you get reduction of the Fermi velocity of electrons, and by a factor of 1 minus alpha. So as I mentioned, the slope of this epsilon tells us the velocity of electron, and if we take the second derivative of this energy with respect to this momentum k, you get the mass of electron, meaning if you take the slope of the velocity, you get the mass of electron, and you see that this mass of electron get enhanced. So let's just take a look at this dispersion of electrons. You can see what I mean by this divergence of this electron-phonon contributions to the electron dispersion. So the yellow curve is the free electron dispersion with a perfect parabola, quadratic dispersion. But the red curves is the new electron or modified electron dispersion by including electron-phonon interaction. So you can see very clearly that there's two singular points right here and here with the relative energy with respect to this Fermi energy plus minus h bar omega bar, which means that the Fermi energy in the neighborhood of the Fermi energy within the range of plus minus h bar omega bar, you get this energy denominator very, very small, and you get a very large enhancement of this electron dispersion. And you can see that this there are two singular behaviors of this new electron dispersions happening right at these two places where this electron energy is either epsilon f plus h bar omega bar or minus h bar omega bar. And there's a very flat regions in between these singularities, and which leads to the enhancement of the density of states. So if you magnify this portion of the electron dispersion and we look at this more clearer picture of this electron dispersion near this Fermi energy, you can very clearly see that there are two singular points in the neighborhood of Kf within the range of plus minus q bar, where q bar is the average momentum of the phonon. And you can see very clearly that there is a flat region, almost flat region, in between these two singular points, and which leads to very narrow energy difference. Okay, so within a very narrow energy difference, the dispersion smoothly increases, and therefore this portion of the dispersion becomes very, very flat. Okay, so from the knowledge of the density of states, we know that this corresponds to the huge accumulation of the electron density of states within this narrow window of delta E, and also Kf plus Q bar or Kf minus Q bar. Okay, so if you calculate density of states, which is given by the derivative energy, number of states with respect to this energy, you get a factor of 1 over 1 minus alpha, which comes from this new dispersion over there, and you can see that this factor is actually bigger than 1, which means that for alpha, which is positive, you get enhancement of the density of states compared to the density of states at Fermi level. Okay, so you could divide this density of states in the electron-phonon system by the free electron density of states at Fermi level. So compared to the free electron density of states at Fermi level, this new density of states near this flat region is actually larger than 1. So you get enhancement of the density of states. So this is very interesting result, which tells us that because of this electron-phonon scattering near this Fermi momentum, there are a huge number of electron states available because they could get scattered by exchange momentum energy with phonons. So within such a narrow window in electron dispersion near this momentum Kf, you get enhancement of the number of states within such a narrow window compared to the free electron states there. And finally, we could estimate this mass enhancement. Remember, the mass, electron infection mass, is defined as inverse of the curvature of your electron dispersion, right? The second derivative of epsilon with respect to k, and you inverse that curvature, you get effective mass of electron. And this electron infection mass compared to the free electron mass is actually larger. You get enhancement with a factor 1 over 1 minus alpha, where alpha is positive value, and therefore the ratio between electron effective mass in the electron-phonon system relative to the free electron mass is actually larger than 1. So there is a obvious a mass enhancement for electrons once the electron-phonon coupling come into play. Okay, so that's most effects due to electron-phonon coupling. And finally, we will make a very important remark on the effects of effective electron-electron interaction, okay, due to electron-phonon coupling, which is very important and crucial to derive the BCS theory of a superconductivity. And we know that for ordinary metals, if you lower the temperature to almost 0 temperature and below a critical temperature Tc, ordinary metals will become a superconductor. And the reason why you get a superconductor is because electrons form pairs, so-called Cooper pairs, and the origin of the Cooper pair formation is precisely due to electron-phonon coupling, and we will derive such a kind of attraction between electron and electron, which overcomes the repulsive Coulomb interactions between electrons. And this attraction between electrons is because of the electron-phonon coupling. And that effective attraction between electrons will bind these two electrons to form the Cooper pairs. And once the Cooper pairs are formed, you get no resistance of electron current, and which is the superconducting current. Okay, so this will be our last topic of this course. And let's take a short break. When we come back, we will make such a final remark on electron-electron effective action, interaction because of phonon. Okay, so let's make a final remark. The effective electron-electron interactions due to electron-phonon coupling. As I mentioned, there will be an effective attraction between electrons because of electron-phonon coupling. But how do we get to this point? Well, let's look at the energy of the electron-phonon system once more. This epsilon up to second order in perturbation is given by this independent, free electron, free phonon kinetic energy epsilon 0 plus this electron-phonon contributions. Remember, there are two terms, right? Okay, but let's just look at the term that involves two electrons, occupation number, Nk and Nk prime, and don't forget the minus sign. So if I just look at this term, marked by yellow, and this is given by this form, which is sum over k and k prime, and the square of the measures element n, and also the product of two Fermi functions nk and k prime in the numerator, but in the denominator we get epsilon k minus epsilon k prime minus h bar omega q. So you could rewrite this, this form in the following fashion, that could just multiply and divide by the same factor in the denominator to actually form the difference between the two squares. The first square is epsilon k minus epsilon k prime, and the second is the phonon energy square. So you could very easily transform this line to the bottom line here. Of course, we need to multiply this whole thing by the excitation value of the minus nk and k prime. So if you look at this, this expression over here and compare this with the Hartree-Fock energy, especially the exchange energy that we already studied long time ago. Remember, the Coulomb interacting electron gas within the Hartree-Fock theory, the exchange energy is given by this form, precisely the same form as this electron-phonon induced electron-electron interaction. So if we simply just replace this yellow box by the Coulomb potential over here, then these two forms are identical, right? So remember, because of the second order in perturbation, we get minus sign in front of this nk prime product. So in this electron-phonon coupled system, we get almost exactly the same form as the Hartree-Fock. Then the interpretation is straightforward because this term is the Coulomb potential. Therefore, this stuff inside the yellow box is interpreted as some kind of a effective electron-electron potential, right? Okay, and you could show that by looking at this cartoon representation or this diagrams of electron-electron scattering by Coulomb interactions or photons or by electron-phonon coupling. So they are really, really similar. Okay, except we get Coulomb interaction in the Hartree-Fock like this, but the effective electron-electron potential due to electron-phonon is given by the stuff inside the yellow box over there. All right? Okay, so you could get a one-to-one correspondence between this Hartree-Fock electron Coulomb potential and the effective electron potential contributed from electron-phonon coupling. So as I mentioned, we can define the electron-electron effective potential as the stuff inside the a yellow box. But if you look at this denominator of the yellow box, and you immediately see that the energy denominator here can go negative as long as the energy difference between two electrons, epsilon k minus epsilon k prime with the absolute value, is smaller than this phonon energy. Suppose this term, this energy difference between electrons, is actually much smaller than the energy of phonons. Then the denominator could go negative. Then the electron-electron effective potential is actually attractive. But this condition is very easy to be satisfied, because when these electrons are at low temperatures, the most active electrons are those close to Fermi surface. And therefore, both k and k prime are very close to Fermi surface or Fermi momentum, and the difference in those energies is expected to be very, very small compared to the phonon energy. So this condition is very easy to be satisfied, and therefore, near this Fermi surface, two electrons could be attractive to each other rather than repulsive. So we can use a cartoon picture to illustrate this effective attraction between electrons. Remember, this Polaron stuff, right? So electrons are dressed up by this, photon cloud or these ion clouds, and these ions could vibrate, which leads to these phonons, and these electron phonons are coupled together. So if you look at the single electrons in the lattice, and it will be dragged by this kind of a positive ion cloud, and the whole thing becomes a more positive charged cloud. So if you look at out of this yellow circle and look at the charge distribution of this single electron, but the dress-up electrons, and you'll see that this the net positive charge accumulated near the center of electron position. And therefore, this net positive charge cloud would certainly attract another electron, the second electron. Well, the second electron actually is elsewhere, and this electron see this positive charge electron cloud over there, and therefore, because of this attraction between positive and negative charge particles, the second electron will come in. So this is a cartoon picture to demonstrate that two electrons are not necessarily repulsive to each other. So in this electron-phonon coupled system, two electrons could get attractive to each other. And this attractive potential could overcome the Coulomb repulsive potential. Okay, so we will analyze this further in the next lecture, that in this electron-phonon coupled system, this effective electron-electron interaction due to phonon is much, much negative than the electron-electron Coulomb repulsion. At least it is more negative than the repulsive Coulomb interaction. So in terms of the absolute value, the absolute value of electron-electron attraction due to phonon is actually larger than the electron-electron Coulomb repulsion. In other words, in the real metals, the electron-phonon induce attraction between two electrons, overcome the repulsive Coulomb interactions between them. And that's the reason why these two electrons like to actually form pairs, and we will study this consequence of this Cooper pairs in the next lectures. This is the starting point for the last chapter, which is the BCS theory of superconductivity for ordinary metals. And because of the electron-phonon coupling, we can have a superconductivity for ordinary metals as long as temperature is lower than the critical temperature. Okay, so that's the end of today's lecture. So we are getting closer to the end of the semester. So I encourage you and I request that you should finish your homework as soon as possible. And they're just 3 lectures away from the final lecture for this semester. So I hope you learned something interesting and useful for your research.